Good afternoon to all of you. In the last class, we learned about basics of latch and flip-flop. Today we are going to learn about sequential circuit design using these latches and flip-flops. Right? Like we saw in the combinational logic, we first defined a function in terms of min terms, and subsequently using the min terms we made an truth table or a k-map table, and then we grouped them and finally made the circuit, and we wrote the equations and finally we made the circuits. And similar approach is done in sequential circuits also. Based on, first we make a state diagram. Based on the state diagram, we make a state table and then state equation and the circuit. So these are the four different steps involved in design of a sequential circuit. So if you see here, let's take an example of making a 2-bit synchronous counter. When I say a synchronous counter, it means that all the flip-flops which we are going to use in this design, they will have a common clock, that the same clock is being applied to all the flip-flops. Okay, so we have yeah, Sachin, we just started the class. We are now going to design a sequential circuit. So to start with, we have taken an example of a 2-bit synchronous counter which is being clocked with the from the same source. That means the clock is going to be the same for all the flip-flops. Okay, so what is the state diagram? Okay, state diagram is the first state which we want is 0 1, then 0 0 0 1, and then 1 0. I think that animation, yeah, 1 0 and 1 1. So we want these these four different states to follow in this particular sequence. So we are going to we want to design this particular sequential circuit. Okay, so whatever procedure I am explaining right now, it is not only applicable to something which is sequentially increasing like this. It could be you can apply the same logic to design a circuit which counts say 0 0, then 1 0, then 1 1 and 0 1, whatever it is. Okay, so you will find that I am just taken an example in which it is moving from 0 0 to 0 1 to 1 0 to 1 1. Obviously, since there are 2 bits here, total number of flip-flops required is 2. So 2 flip-flops. So one is a MSB flip-flop and one is an LSB flip-flop. So initially both the flip-flops will be 0 0. Then the LSB flip-flop flips to 1, then that comes back to 0, and the MSB flip-flop goes to 1, and then the last state 1 1. So this is what this is what we want to design. This is a simple counter which is increasing by 1 0 1 1 0 and 1 1. Okay, so we'll try to understand how to design this circuit. Okay. So this is the present state. Like there are 4 different states: S0, S1, S2 and S3. So 0 0 is the state of the flip-flop, right? The next state will be 0 and 1, because now we are saying this is the state, this is known as the state diagram. From the state diagram we are going to make a state table. From 0 0 it is going to 0 1. So from 0 0 to 0 1, and from 0 1 to it is going to 1 0, from 1 0 it is going to 1 1, and from 1 1 it is going to 1 0. So QA and QB, these are 2 different flip-flops. Okay, this is the present state of the flip-flop, this is the next state of the flip-flop. So we make a state table like this. Okay, so once we make the state table, then we need to know what is an excitation table. Okay, now what is an excitation table? Like we know for JK flip-flop, for 0 0, the output will remain the same when the clock comes, right? The whatever was the previous state, it will remain as QT. For 0 1, irrespective of what was the output, it will become 0. and for 1 0, irrespective of what was there earlier, it will become 1 for a JK flip-flop. And if it is 1 1, the output would toggle. It means if it were a 0 earlier, then if 1 1 with J and K being given 1, and when the clock rising edge of the clock, this is going to become, if it is 1 it will become 0, if it is 0 it will become 1. So this is known as toggling. So this is the characteristics table of the JK flip-flop. Now we are going to design this particular counter using a JK flip-flop, and that is the reason we should know this table. Now if you see the excitation table, suppose this is the now I am thinking from a different angle. This is the present state, and the next state I want as 0. Then what should be 0? J and K values. Like J has to be 0, K can be anything. Okay, why I am telling K can be anything is, like if it is 0 and K is also 0, 0 0, it remains the same state. So 0 to 0, it will remain the state. If K is 1, 0 1 is also 0, so that also satisfies the condition. So I can have input 0 0 or 0 1, and still I will get the output as from 0 it will remain 0, and that is why I am writing J is equal to 0, K is equal to don't care. Don't care means it can be either 0 or 1. Is this understood? If this is understood, everything in this particular lesson will become pretty easy. Is this understood? Yeah, Sachin, Ritika, how did I get 0x? Yeah, Kishan, is that okay? Yeah, okay. So now if you see here, suppose this previous state is 0 out here, and then now the next state has to be 1. Okay, so what should be the value of J and K? Now if you see here, this is 0, it has to toggle to 1. So one option is to give 1 1, right? What is the second option? If you give 1 0 also, the output will go to 1. So that is why I write it as 1 into x. Okay, so if I give 1x, okay, 1x means don't care. So if I give 1x, then why I am writing don't care conditions here is, when we know that don't care, we can club it finally. When we make the K map, we can club it either with 0 or 1. So that gives me more flexibility. If I write 0 0 here, so that will tie my hands down and the flexibility will be lost. So that's why I am writing using these don't care conditions here out here. Now I have a 1 0 here. Now if I look at 1 0 here, I have to the previous state is 1, now it has to go to 0, right? So if you see, I give 0 1, so irrespective of the previous state it will go to 0, and if I give 1 1 also, if it is 0 it will toggle, it is toggle. So I can write, so these are the 1 1 and 0 1, so it becomes x into 1. For 1 0 it becomes x into 1. And suppose if it has to it is 1 and you require continue to remain 1, okay, in the next state Q continues to remain 1, that is our requirement. In that case, if I give 0 0, it will maintain the state, or I give 0 1 also, or if I give 1 0 also, it will remain 1, right? So this is 0 or 1, this has to be 0. So I put a don't care condition and 0. So this is known as the excitation table. So from this state, okay, this is the flip-flop, this is the present state, this is the next state. Now for the next state, for 0 0, it has to go to 0 1. For it to go to 0 1, this is the MSB. QB is from 0 to 0. So for 0 to 0, what is it? It is 0x. So I am writing 0x here, whereas QA is changing from 0 to 1. So 0 to 1 is 1x. So I am writing 1x out here, right? So this is 1x. I am writing 1x here. In the next state, I have S1 out here, right? S1, and then it is going to S2. So this is 0 1 here, okay, that 0 1 and 1 0, that means this is changing from 0 to 1. Okay, the MSB is changing from 0 to 1 out here, correct? So and this is changing from 1 to 0. So I have for 0 to 1, if I go back here, for 0 to 1 it is 1x, so I have written 1x, and 1 to 0 is x1, so I have written x1. Now the next state is from 1 0 it has to go to 1 1. So 1 1, 1 1 is x0, right, and 0 1 is 1x. Okay, so this is the this is coming from the previous state. So this table requires to be remembered. And then finally I have 1 1 here, right, and the next state is 0 0. So I write an x and 1 here, and x don't care, and 1 x indicates don't care, so x and 1 here, right. So I have this now JK. This is the MSB, JB, KB, JA. Okay, there are two flip-flops, and these are the two JK flip-flops, and the inputs now for different state conditions are given here. Now I have to write this, map this with respect to the states. Now if it is 0 0, then for the next state I have to give j is equal to 0, k equal to b. For 0 1, and now I take let me take only JB. Okay, JB for implementation of JB. For 0 0 it is 0 0, 0 1 it has to be 1 here, 1 0 I don't care, 1 1 don't care, right. So if I see here, I can simply write it as an QA, right. So this is don't care. So this is 0 0 1 1, and then these are don't care conditions. So I can write JB as QA. I can also make an Q map. There are two variables out here, right? This is two variables, and this is the output JK. So if I make an two variable K map, still I will get the same equation. So here JB is equal to QA, right? Similarly KB, these are don't care conditions. This is 0, this is 1. So the output is also 0 1. So I can write KB is also equal to QA, right. Now if I see here, if you see here, it is 1x 1x. So I can put these don't cares as 1. So this entire thing becomes 1. Similarly k is also x, I don't care. So if I put 1 1 here, the entire thing becomes 1. So JA is equal to 1 and KA is equal to 1. So if you see here, now to implement this circuit, this is the MSB where J was QA, right, J here JB was and KB was QA. This was the MSB out here, this was MSB, this was LSB. So here this is the LSB where we have given 1 1 out here, and you have put in QA for both J and K. So now once this clock starts coming in here, this will go from 0 1 2 3 and come back to 0. Is this how the procedure clear to all of you? How to make an sequential circuit, how to design a counter? Okay, let me go back and quickly tell you once again what we have done. This was the problem statement. Okay, we had to design a counter which will count 0 1 2 and 3 sequential, 0 1 2 3. It has to count like this. So what is the first? So obviously here it is 0 0 0 1. So there has to be two flip-flops because there are 4 different states. So 2 flip-flops are required. First condition. Now these are the 2 flip-flops. So if it is 0 0, the next state is 0 1. If it is 0 1, the next state will be 1 0, and 1 0, the next state will be 1 1, and if it is 1 1, the next state will be 0 0. So this we made this table which is known as the state table. Okay, so after making the state table, now this is the excitation table. Okay, so this is the excitation table of JK. Now for 0 0, for it to go to 0 1, what should be there are two flip-flops. This is one flip-flop, this is the second flip-flop. This is the output of the first flip-flop, this is the output of the second flip-flop. This is the LSB and this is the MSB. So these are the inputs of those two flip-flops, JK inputs. So from 0 it is making 0 here. So I write 0x. So because 0 to 0 is 0x, I get it from the previous. So 0x. Similarly, this is making from 0 to 1. So I make these 4 conditions for the 4 flip-flops, and then I write the formula for this, I make the state equation for JK, JB, KB, JAK. They are the two flip-flops and 4 inputs are to be given. For each one of them, the input variables are the states only. Okay, you have an QA, QA bar, QB, QB bar. So these are the two inputs. So based on these inputs, we derive what is the equation for JAKB, JAKB, and accordingly make this circuit. So it will start counting the same. Okay. Now if you see here, say if I have to make a counter which is 0 0 and then 1 0 and then 0 1. Okay, what change is it going to make? Here it is going to make a change now. Now this order will be different out here. If this order is different, then these also will be different. If these are different, then what happens? Then the equations which you get will be different. So accordingly you will get a circuit. So it is not necessary that this should sequentially increase. Okay, you can have any random series also, and also not necessarily you have an like 4, you can have only 3 also. After 3 it is coming to 0, you can still have that. Now also you can have like 6 7 states, like after 1 1 0 0 and then 0 1 and then 0 0. Okay, those kind of combinations, whatever be the state, the design remains very simple. First you have to make whatever is the required, you make an state table like this. Okay, once you make the state diagram, you transfer it into a state table. From the state table, you get the what are the, depending on the flip-flops you are using, you make this table, and from here you derive the state equations, and from the state equations you make the circuit. Okay, the procedure is simple. We will take one or more examples, then things will be clear. Okay, now that the earlier design we just saw was made out of JK flip-flop. You can use a D flip-flop also, right? So if the next state is to be 0, okay, then for a D flip-flop, the input will be has to be given 0. If the next state you want 1, then input has to be given 1. Okay, so there is no don't care and nothing. For D flip-flop, whatever next state is there, you need to give that as an input. So this is an straightforward. Similarly, if it is an for an toggle flip-flop, if you are using a toggle flip-flop, if you put 0, the previous state remains. If it is 1, then it will toggle the output. Okay, so based on these characteristics, accordingly the excitation table will change slightly. So accordingly the circuit also will change. Okay, so let's do the same example which we did earlier, now implementing it with D flip-flops. Now it is 0 0, then it has to go to 0 and 1 in the next state. Okay, if it has to go to 0 and 1 as a next state, DB will become 0, because I want 0 here, and 1. So this is 1. So this is straight away the same thing, which DA and DB is the next state itself. Okay, for 0 1, after that 0 1, 0 1 has to now change to 1 0. So DB and D0, DA will be 1 0. Then the next state from 1 0 it has to go to 1 1. So this will be 1 1, and then from 1 1 it has to go to 0 0. So it becomes 0 0. So you understand how this table is written? It is plain and simple. Is it okay, Ayushi? Are you able to get it?
Yes, sir.
Yeah, okay, good. So now I write these states, and then I write what is the DA and DB for the next state. Now I have to write DA and DB in terms of QA and QB. Now if you see here, if you compare these two, right, and what is if you see here, it is 0 0 it is 0, 0 1 it is 1, 1 0 it is 1, 1 1 it is 0 out here, right? So just seeing these two, I can write the value of dB as QA XOR QB. Okay, so you might say, sir, if I am seeing, if I don't get any visual clue, then simple, it is two variables, right? It is two variable. You make an K map and you write dB in terms of Q and QB, right? If you write that, you will get, and or if you write a Boolean expression corresponding to this, right? It is 1 and 1. Okay, 1 and 1. What is 1 and 1? It is Q bar A and QB bar QA and QB QBAR, right? You then still you will get QA exclusive or QB, right? So visually also we can see. Otherwise, if you write the Boolean expression, we will get it, right? Here also similarly DA, if you see here, it is 0 0, it is 1. 0 1 it is 0, 1 0 it is 1, and 1 1 it is 0. So if you observe it here, D, when it is 0 it is 1, right, and it is 0, it is 1 here, it is 1 here, it is 0 here. So 0, it is 1. So it is just DA is nothing but QA bar, right? Otherwise, if you are not getting any visual clue, what is this DA? It is an QA bar, QB bar, and here one QA bar, QB. So if you take a QA bar common, QB bar and Q plus QB will give you 1, so it will give QA bar. So if you write an algebraic expression also, you will land up in the same solution. Now DA is QA bar and DB is QA bar QB. Now the same counter, if I am implementing here, now it will look like this, right? So QA is QA bar. So QA bar is given as input to this flip-flop, and DB is QA bar exclusive or QB. So I have an QA coming here and a QB coming here. There is an exclusive OR gate, and I am doing an exclusive OR and giving it to DB. So the same, this also will count from 0, 1, 2, 3, again go back to 0. So this is how we can design a sequential circuit using D flip-flops. Okay. Now, so like I said, I can have an design a mod 3 counter. So when I say a mod 3 counter, so it means it doesn't mean it will count till 3. When I say mod 3 counter, it means it has got 3 states. Okay, 0, 1. Like these are the 3 states, so 0, 1 and 2. When I say mod 5 counters, it means it will have 5 unique states. It will not count till 5, it will count from 0 to 4. Okay. Now this is a mod 3 counter, 0, 1, 2, and it has to go back to 0. So in case the flip-flop for any reason it come during switching on and off, the previous state is 1, 1, then it should also come back to this loop. Once it comes back into the loop, it will be within the loop. For some reason, if it goes to 1, 1, it has to come back to 0. So I have to design this particular counter. So what do I do? Again, it is simple QA, QB, right? The next state is for 0, 0, it is 0, 1. For 0, 1, it is 1, 0. For 1, 0, it is coming back to 0, 0. So for 1, 0, it is coming back to 0, 0. So for 1, 0, it is coming back to 0, 0 out here. And for 1, 1 also, it is coming back to 0, 0. For 1, 1 also, it is coming back to 0. So I make this. Okay. Now I can, if I have to implement it with an JK flip-flop, then I write JA, KA, KB. Now here, if you see here, QB is 0, 0. So I write 0x. Okay. This is coming from the characteristics table, right? Here. If I go back here for JK flip-flop, here for 0, 0, it is 0x. So from this table, I am writing it here 0x. So I write these tables. Now JA, K, JB, K. Now these have to be written in terms of QA and QB, right? So you can make an K map also here if you are not able to get any visual cue. So QA, QB. And I write this, it is 0, 1, double 0, 1 and XX. So I can group these two. So it will come as QA, right? And for KB also I have to make one more K map. It is XX11. So XX11 is nothing but a 1 only, right? So 1. So you see here. So here I have just shown the K map boxes also, so that in case you don't get any visual clue, you can make this K map and do that. Right, and for JA also it is Q bar 1, 1 we have clubbed it, so you get a Q bar, and for the last one it is again a 1. Is this clear to all of you? Yeah, Kishan, is it okay? Okay. So once having done that, then we put these two flip-flops and accordingly. So if you see here, see here, B is the MSB. Okay, so the B is the MSB. So it is an QA and 1 no, for JN. So it is an QA and Q bar A and 1. I think Q bar A. It has to be Q bar A, or is it QA? No, Q bar B. Okay, sorry. Here the LSB is shown here, MSB is shown here. So we need to be in this particular diagram. This is the LSB, this is the MSB. Okay, so it was picked up from one of the textbooks. So that's why this is the LSB and this is the MSB in this particular case. So this is how these connections are given. Based on this, whatever solution we get here, that needs to be connected as it is. Oh, this is the LSB, this is the LSB, here it is the MSB here. It is doesn't matter, it is just the way it is placed here. Okay, you can redraw it also accordingly, right? So now with each clock it will continue. It will give you as the 0 0 and then 1 0 0 1 and 0 0. So it will count like that. Okay, so now here we assume that it will be synchronous. Both the clocks are being given the same clock till now. Here all the clock was same for all these circuits. We can have something known as asynchronous counter also, right? The asynchronous counter means it is all the flip-flops are not given the same clock. Okay, now this is an 2-bit asynchronous counter. Okay, it will count from 0 1 2 3 and then come back to 0. So how does it happen? Let's just see. Now if you give J and K here 1 here, now here also this is the LSB, this is the MSB. Okay, on the left hand side is the LSB here. J and K are given 1 out here, right? So it will toggle. So when the clock is coming, the first positive here it is showing this is a negative edge triggered flip-flop. Okay, so if you see here, when the clock is falling, okay, it is going from 0 to 1, and again the clock is falling, it is coming from 1 to 0. This clock is falling, it is going from 0 to 1, and again you have a clock falling from 0 to 1. Okay, now this data, okay, this data which we are getting out here is being given as a clock here. Okay, in this particular circuit, right? We are giving it here, right? Then what happens if you see here? This is now this 0 0, right? Initially it is 0 0. This is positive going edge, so it's not triggering here. This is the negative going edge, so it is going to trigger here, right? So it is going making a change here. Now this positive going edge, nothing is happening. This negative going edge, it is again making a transition. Now if I read this, it is 0 0 0 1 1 0 and 1 1. This is the MSB, this is the MSB, this is the LSB. So now if you see, again it is a counter, right? 0 0 1 1 0 1 1, again 0 0. So this is also an mod 3 counter, where it is mod 4 counter, where it is counting from 0 1 2 3, again coming back to 0 using 2 flip-flops. Okay, it is known as asynchronous counter because we are not giving the same clock. This is being powered from this clock is being given from the output Q out here. This is the LSB, this is the MSB. So this is known as asynchronous counter. Okay, now I can have an asynchronous counter with 3 flip-flops also, right? So if you see here, so it will count up to 8. Okay, so initially it is an 0 0 0 out here, 0 0 0 here, right? Now if you see here, this is the LSB. See, it's written LSB out here, this is written MSB. So with every clock, right, with every clock this is going to change. 0 to 1 1 to 0, 0 to 1 1 to 0 1 to 0, this is going to change. What about this? See, it has to be for up counting, it has to be negative edge triggered. Okay, so whenever QA is being given here, QA is going to be from 1 to 0. This will make it a transition 0 to 1 here. Okay, so if you see here, D is okay. Here D is given here. Here again a Q bar is given here, right? If you put a Q bar here to D, it will act like a T flip-flop, right? If it is 0, it will change to 1. If it is 1, it will change to 0. So whenever you take a feedback from Q bar and put it into D, it will act like a T flip-flop. So all the three will act like a T flip-flop. T flip-flop means toggle flip-flop. If the D is 0, Q bar will be 1. So when the clock comes, it will become 1. If D is 1, Q bar will be 0. So 0 will be fed here. When the clock comes, it will. So now here there is an error. It is not the positive edge of the clock, it's a negative edge of the clock. Okay. So this counter will work, will go in this manner only if it is a negative edge of the clock. Okay. So 0 to 1. So when it is going from 1 to 0, no, this will trigger the next flip flop. Similarly, if you see it is 1 1, here it is going 1 to 0, so this will trigger here, right? So if you see here, it will count from 0 1 2 3 4 5 6 7 8 and then come back to 0 0, right? So so if you see here, this has to be a negative edge triggered. So in counters we will again revisit this. If it is a negative edge trigger, if it's a positive edge trigger, it will count in the reverse direction. We'll see that. Okay, timing, just understand, a synchronous counter, it has to be negative edge triggered, and if you give like this will be the MSB, this will be the middle one, this will be the LSB, most significant bit and the least significant. So it will count sequentially from 0 to 8. Okay, this is another form of this is an another form of counter which is known as asynchronous, because it is not the same clock which is given out here. It is the clock of Q of one state is given as a clock to the next state. Okay. Now we can also design an asynchronous mod-5 counter. Like here we designed synchronous mod-3 counter, like only 3 states were there, the fourth was not used. Similarly, in asynchronous also, suppose I have 0 1 2 3 4, only 4 states are required and a fifth is not required, so only 4 are there. But then it will get, we have to cater for the fifth state. It will come to the fifth state momentarily and it will come to 0. Whereas in the synchronous design, from 4 the next state we can write to 0 0. But in an asynchronous counter we can't do that. We will have to introduce a temporary state, fifth, which will, the flip flop will not remain here. Okay, it only means the moment it comes to this state, it has to go to 0. So that is the difference when we design an asynchronous counter. So if you see here, when it reaches 5 is what? 1 0 1, right? So 1 0 1 is 1 0 and then 1 here. So I put an AND gate. For this 0 I have put an inverter. So this will become 1 1 1. So whenever I get 1 0 1 here, so this AND gate will trigger, and what it will the output of this AND gate is given to the clear inputs of all the 3 flip flops. So all the flip flops will go to 0. So it will normally, we have given this Q here, this Q here, right? So it will start counting like 0 1 2 3. It will reach 5 momentarily, and the moment it reaches 5, okay, the count reaches 5, this AND gate will clear all the input. That means it will go to 0 0 0. Again it will start counting 0 1 2 3 4. Okay, so now you can see the problem with this asynchronous counter is there will be a small glitch, whereas in synchronous counter we don't have these kind of glitches. Okay, this is again the asynchronous counter. Here we used D flip flops. Here you can use a JK flip flop, where again all the J and K are tied to VCC. That means they will act like a T flip flop. So whenever you have an 5, so you have an see 5 is 5 is what, 1, and this 0, if you see from 0 to 5, there is only one condition where 1 and 1 will be high. So you don't have to take actually this 0 also. You can take an 1 from here and 1 from here, and then put a NAND gate, because here it is in a clear bar. So you put a NAND gate here, and you can clear all the 3 flip-flops. So even this configuration is this is also one method of using making an asynchronous Mod-5 counter using JK flip-flops. Okay, like I said, because if you see the count, okay, 0, 0, 1, 2, 3, 4. So only in 5 I have 2 ones, MSB and LSB. Here we don't have, right? Both MSB and LSB. Here only the LSB is there. Here middle. Here only. So this is the state where 1 1 both are 1 here, right? So this is the only state. So that is the reason if I take only Q and Q bar also, that is good enough. I don't have to take 0 from here. Even this is good enough. And then I am putting a NAND gate, because this is here I have a JK flip-flop which is using an active low clear signal. So that is why I am using a NAND gate. Okay. Now if you see the waveforms also, so whenever it reaches 5, there will be a small spikes here. Okay, these spikes, this is shown here. So that is a problem with the asynchronous counters. Whereas if you are using synchronous counters, then these kind of issues will not be there. Okay. Now there is another problem with asynchronous counter. As long as the count is sequential, we can work it out easily, right? Okay, it can count wherever you want to stop the count. You make a particular combination. Like here we are saying mod 5. You say mod 8 counter. So whenever it is 7, you detect that and clear. So as long as the count is from 0 to 7 or from 7 to 0, the reverse also, there is no problem. Okay, but if I have to count, say 1, 3, 2, 7, 6, like that, then it is difficult to design an asynchronous counter. Whereas for a synchronous design, right, synchronous design, this can be anything, right? And it can be 0, 0, 0, and then 1, 1. And then 1 0, it can come back to 0, doesn't matter. Okay, you just have to make the state chart out here, then make a state table, and accordingly design the circuit. Okay, so the procedure remains same. Okay, for asynchronous, it is always, if you give like this, it will count in a particular ascending order or descending order, and you have to give a reset. So that is a limitation of having an asynchronous counter. Okay, so we'll take 10 minutes break. It's 42 now. So 55 we will again assemble, and then we will take on another small topic. Okay, thanks a lot.